All right, so hopefully you wrote down your conjecture for second order necessary conditions. Here's one way to say second order necessary conditions is that if we're at a local minimum, then the Hessian is positive semi-definite. And if we're maximizing, then when we need it to be negative semi-definite. So a question is, why do I say positive semi-definite? What about positive definite? If the Hessian is positive semi-definite, shouldn't that guarantee that we're at a local minimum? So think about that for a sec. Why does it not guarantee we're at a local minimum? Well, if it's semi-definite, that means that there's some direction you can move in that you get a zero change to second order, right? That matrix product happens to be equal to zero, which in some sense seems like it's saying instead of a bowl, you have kind of a long trough like this, and you can move along the bottom of the trough, and that would be like ties for the minimum. That doesn't seem bad, but the problem is the Taylor series is is an approximation right at this point. It's saying from the view of this point, it looks like it's a long trough, but it's possible that if you move away from the current point, the curve actually moves away from the Taylor polynomial. It usually does, and it could actually curve downward to kind of third order or fourth order. And here's an example of a function that we like to use in pure math that has zero derivatives of all orders at the origin, and yet this one is actually shaped like this, so it would be a local max instead of a local min, even though its kind of Hessian would be positive semi-definite. So apparently saying semi-definite does not guarantee a local minimum, so what would you guess is the second order sufficient condition that would guarantee a local minimum? Well, it's basically being positive definite, or if we want to maximize, then being negative definite. So our second order polynomial looks like this for maximizing, or this for minimizing. Notice the order switch between the if and then for sufficient conditions and necessary conditions. And I actually got that mixed up, didn't I? This one is the necessary condition, and that one is the sufficient condition. There we go. So one starts out, if we know we're at a local min, then we can say the Hessian is positive semi-definite. But if we want to prove that we're at a local min just by looking at the Hessian, we actually need it to be positive definite then, right? So what questions still need to be answered? Why, like, can I just look at the Hessian and say this is positive semi-definite or positive definite? We'll get to that in the next video.